Our next presentation and last for today is from Marcel Ferrari from ETH Zurich and Nina Mujkanovic from CSCS.
Hello, everybody. My name is Marcel. I'm from the Department of Mathematics at the ETH. This is my colleague Nina from CSCS. And today I wanted to present some of the work that we've been doing as a collaboration between ETH and CSCS on developing a practical performance model for large-scale distributed GPU workloads. So, as Brian mentioned, I will be giving this presentation with Nina. And so I've created sort of two short table of contents so that I give you some context on what we'll be discussing before we get into it. I will be talking about the mathematical modeling part. I want to give a bit of an introduction to and motivation on why we need performance modeling. I will be discussing the profiling metrics and sort of the data that can be collected from GPUs. And then I will start going into more of the mathematics of it, starting with classic roofline analysis. I'm sure that many of you have seen this already. And we will be extending this model by incorporating different things. First of all, we will be incorporating dynamic performance and intensity. So we'll sort of make time a first-class citizen in this model. And then I will show you how you can actually derive roofline analysis as a graph-based problem. And from there, I want to spend a few minutes talking about bottlenecks and efficiency. How can we quantify this given our performance model? And finally, just explain some of the limitation and the future work so that, I really want to stress out what this model can do and what it can't do in order to, avoid misleading statements. From Nina's part, she's going to be talking more about how performance analysis is handled at CSCS. So she will start, with a bit of an introduction to the CSCS ALP system. She will explain some practical use cases for similar performance models. She will touch on the challenges of doing profiling in sort of distributed environments, as well as discussing some of the existing tools, their capabilities and limitations. And then just give sort of an outlook of the future of performance analysis on the ALP system. Okay, so let's get straight into the mathematical modeling part. Before I start talking math, I wanted to give a bit of an introduction. So where does this whole idea come from? Well, at the time I was working part-time at CSCS, and a colleague of mine came to me and told me, hey, I ran this tiny PyTorch experiment where he trained a small neural network with two different implementations of the Atom optimizer. One was the standard Atom that you have in PyTorch, and the other one is a fused implementation of Atom, which does some further optimizations to do more computation on the GPU. And what he noticed was that fused Atom was running 30% faster, so the time to solution was improving. But at the same time, both runs were reporting static 100% GPU usage. And so the question now was, okay, why doesn't GPU activity reflect sort of the performance difference? Intuitively, one would say, okay, I have higher performance, so I expect that this will give higher GPU utilization. But the reality is actually that GPU utilization is a very coarse metric that signals when any component of the GPU is doing something. And the result is that you have a very misleading interpretation of what this value does, and a lot of people just look at that and say, oh, okay, GPU utilization 100%, so my workload is very efficient, which is unfortunately not the truth. So this is what really started this whole process. And once you get into it and actually look at what GPUs offer, it turns out that GPU utilization is not the only quantity that you can extract. Actually, there are hundreds of performance counters that you can query from Nvidia GPUs. And all of them have the same problem. The raw metrics are just difficult to interpret. You need knowledge about sort of how the architecture works, and you need low-level hardware knowledge to understand what is going on. And this is where quantitative performance models can really help us out. They can tremendously help users interpret performance in a bit of a more, let's say, architecture agnostic way, so that they don't have to deal with all of the tiny details of the hardware. And there are mainly two ways that performance models can really help. Number one is identifying performance bottlenecks. So essentially, you ask yourself, okay, what is the component in my hardware that is limiting or imposing the tightest limit on performance for my workload? And once you have that, you can ask a follow-up question. Given a set of sort of performance constraint for my workload, how efficient is my implementation? So how close am I getting to these theoretical limits? And the idea is that if you combine insights about how your workload works and what it is doing with this bottleneck analysis, as well as an evaluation of the efficiency of your implementation, you can really get to a point where you're doing targeted and very effective workload optimization instead of having to brute force everything or just trying without really understanding what's going on. Now, I was talking about these performance metrics, and specifically NVIDIA GPUs offer a quite cheap way to track hardware activity via these sort of performance profiling metrics. And the idea is that you can query GPUs for point-wise averages of these quantities over a tiny sampling interval, or tiny depending on what the scale of your workload is, but over a given sampling intervals, delta t. And these metrics often represent both an average over time, but also an average over, for example, all of the SMs in a GPU, so all of the streaming multiprocessors. And before even talking about performance, this is a very important thing. These values are not instantaneous. So for example, an SM activity of 0.2 could mean 20% of the SMs working at 100% of activity for the full interval, or 100% of the SMs at 20% activity over the interval, or 100% at 100% for 20% of the time, or a combination of these states. So this is also why it is quite tricky to understand what is going on from these metrics. Okay, so I just want to give a few examples of the type of data we're working with. Of course, this is not the only things that you can query the GPU, but they're definitely among the most interesting things that you can sort of read. The first one is SM activity, which tells you sort of the fraction of time at least one warp was active on a multiprocessor, averaged over all the SMs. You have occupancy, which is the fraction of resident warps on an SM relative to the maximum warps supported. You have floating point engine activity, which tells you essentially how hot your tensor core or floating point engines are running. You have memory bandwidth utilization, which quantifies how much data was being moved between memory and registers. And finally, you have, for example, transfer bandwidths, which tell you the rate of data transmission over PCI Express or NVLink, depending on your hardware setup. And so sort of the most simple and straightforward thing you can do is you run your workload on a GPU and you track these values over time. For example, here we have some mystery time series data from some unknown workload. And the first thing I want you to look at is, well, before getting into this, what I'm reporting here is GPU utilization, SM activity, tensor core activity, and memory activity. And so the first thing I want you to notice is that GPU activity is fixed at 100% the whole time. So effectively, it tells you nothing. You don't know anything about what the workload is actually doing under the hood. Instead, if you look at, for example, SM activity, tensor core activity, and memory activity, you can see that there are some periodic patterns that happen throughout the workload. And this could mean, for example, that there are alternating phases of compute and data transfer, for example. Now, specifically, if you notice, there are periodic drops in memory activity that are coupled with sort of spikes in the tensor core. That would be the green and red lines, right? When the red line drops, the green one spikes. And this, to me, suggests perhaps compute-bound regions, where you're doing a lot of compute and doing very little memory operations, so you're in a compute-bound regime. But in general, it is very difficult to quantify what the exact bottlenecks or the efficiency is based on this data. I mean, as you've seen, I can extrapolate some insight, but I wouldn't exactly know whether it's truly compute or memory bound or what is happening in reality. And this is why we really need an objective performance model to give us an idea of what the true efficiency and bottleneck is. Now, I mentioned that I was going to talk about roofline analysis. I'm sure this is a very traditional sort of performance model that many of you, I'm sure, are familiar with. Essentially, what the roofline model says is that the performance of a workload is either compute bound or memory bound. And what this effectively means that P, our performance, has to be smaller or equal than either the peak performance of whatever hardware you're using. For example, this could be how many flops per second your GPU can do in theory if you run it at 100%. But also, it could be limited by the memory bandwidth via the operational intensity. Now, the operational intensity essentially expresses how many floating point operations you're doing per byte that you transfer from memory to registers. So if you have a lot of operational intensity or high operational intensity, you know that you're transferring very little memory or very little data from memory to registers, and you're using that data to do a lot of computations, and very likely the bottleneck will be how much compute can you do on your hardware. On the other hand, if you have small sort of intensity where every byte you move use very little in terms of computation, then very likely the bottleneck is not going to be how fast you can compute, but rather how fast can you move this data from memory to registers. And this model is great. It's very intuitive, but it has some problems. The first of which is that it has a very strong assumption about operational intensity and performance. It assumes that both of these quantities are fixed static points that are only kernel dependent. To give you an example, if you're building a performance model, what you could do is, for example, let's say you're taking matrix multiplication, right? You know how many operations are required to do matrix multiplication, and what you can do is you sit there, you look at your implementation of the matrix multiplication kernel, and you count how much data you're moving per operation, and that's how you derive your operational intensity. Then you run your kernel, you time how long it takes, and you know sort of the performance that you're getting. And this means that your whole workload is reduced to a single static point on this graph, either in the compute bound region or the memory bound region. This is fine if you have a very short or very homogeneous workload, but when you're sort of scaling up to larger workloads, this completely breaks down because it's unrealistic to assume that any type of machine learning or scientific computing workload will have a uniform performance and sort of uniform characteristic and intensity and whatnot during the whole execution time. So this in itself is already a deal breaker in a sense. We need to relax this constraint in some way. And that's sort of the first idea, to use dynamic quantities instead of static quantities. So again, we relax the operational intensity to be a time-dependent function. And if we look at the performance metrics that we have, we notice that actually we can use these metrics to estimate the operational intensity and the performance at various time points in our workload over these tiny delta t intervals. So the average performance over our little interval is just the peak theoretical performance. So for example, for a H100 GPU, it should be like 60 teraflops, multiplied by the activity of the given floating point engine, depending on whether you're doing 32-bit, 16-bit, or whatever precision, or if you're using a tensor cores. Of course, your peak performance changes, but the idea remains the same. The percentage tells you how much you've been computing, and then you multiply by the peak to get the actual number of flops. And the same you can do for the memory traffic from memory to registers. Same idea, you take the memory usage and you multiply it by the peak sort of memory bandwidth in order to get an idea of how much data you're moving around. And what is interesting is that if you estimate the intensity, well, you would technically need point-wise values, right? Because you need to integrate this true performance and the transfer functions. But it turns out that since we have these average values, well, the computation is equivalent to just taking the ratio between our averages. So essentially the takeaway here is that we only have access to average values for performance and data transfer, but the actual intensity that you can compute is an exact quantity. There is no approximation or averaging in that quantity, simply by how the mathematics work out. And essentially what this gives you is time series data for both the performance, which again we can approximate via these averages, and the intensity. And if you take all of these samples for workload and project them onto this performance intensity plane, you get what I like to call a roofline distribution model. It is the same type of model that we had before, but now you can see that a workload is not represented by a single static point anymore, but rather by a distribution of samples over the workload sort of length. And this is, again, the data that you obtain from the tiny mystery application of before. And you can see that, as we suspected, some samples are in a compute-bound region, but other samples are in a memory-bound region. And this depends on where exactly you're looking in your time series data. And now we get to how we can derive roofline analysis as a flow graph problem. So imagine you have this very simple linear graph where you have memory, registers, and this sort of virtual node called compute performance. Now, we can model this as a source sink problem, where essentially we have a data source from memory and a compute performance virtual sink. It's not, of course, it doesn't make sense. It's not a true sink because there's no data movement in terms of compute performance, but we keep it there just to make the mathematics work out. Now, there are two bounds, of course, two theoretical upper limits, which are the sort of bandwidth of the memory and the compute performance, peak compute performance of your GPUs. We know that these are limits that we cannot ever go over across. And then what we have is the sort of measured data transfer as well as the measured performance. So you can see that sort of by looking at this graph in the following way, you can already sort of define some trivial constraints. And those are that, well, the performance must be smaller than the peak performance or peak compute capabilities of my GPU, and the data transfer must be smaller than the sort of memory bandwidth, because that's simply sort of the peak that the hardware can give. Now, these are not very useful constraints, but there is one additional thing that you can use. The idea is that we want to enforce continuity of flow, in a sense, between edges. So all of the flow that we observe from memory to registers has to be equal to the performance going out. But the catch here is that there is a scaling unit in between, and that is precisely the operational intensity. An intuitive way of seeing this would be, imagine you have a tube with some fluid flow flowing across the tube, and the tube has two different cross sections. And of course, you have some velocity on one part and some output velocity. And of course, you need that the output velocity has to be proportional to the input velocity, but scaled depending on the sort of ratio between the two cross sections of the tube, in a sense, to make sort of a physical analogy. Now, what we can do here is update the second constraint in our system and say, okay, we know that B is smaller or equal to beta, so if P is equal to I multiplied by B, then that must also be smaller than I multiplied by beta, right? And if you combine everything, this is exactly what roofline analysis tells us. So this is an equivalent formulation of this roofline analysis problem. Now, before I go forward, I want to introduce this new quantity called transfer intensity that I need in order to build this model. Essentially, it is very similar to operation intensity, except it just quantifies the data movement or the ratio of data movement between two connected edges. Essentially, the transfer intensity from the edge I to the edge J is simply the ratio between flow J divided by flow I, where, of course, Fi and Fj are these sort of measured data flows. And again, it does serve a similar role to operational intensity. The idea is that we can enforce this similar sort of this continuity constraint where the flow J is equal to the flow I multiplied by this sort of transfer intensity. And it is a unitless ratio of data movement. It's a little bit different, but the point is that it is used to enforce this sort of continuity constraint. Now, the next step is, okay, we derived roofline analysis by looking at a very simple linear graph. Well, nothing is stopping us from using a different graph that incorporates more information, and we just solve the problem in the same exact way. So right here I have one possible approximation of a gracehopper node in the Alp system as a flow graph. We have a source that is comprised of that comprises 4 different components. Of course, the slingshot network, as well as 3 other gracehopper nodes which are connected via NVLinks. The node itself has a host memory, has a GPU memory, and as well as registers, both on CPU and GPU, and there is one single sink, which is the sort of compute performance virtual sink that we were discussing earlier. Now, the first step is to just look up the datasheet for this node and plug in essentially the constraints that are imposed by just the peak performance of the hardware. So all the betas are sort of peak performance constraints. All the F values are the actual observed data flow. And at the end, we have pi and p, which are essentially the peak performance of the CPU and the GPU versus the actual observed performance of the GPU and the CPU. And from here, what we do is we define a transfer intensity on every one of these nodes. And we solve exactly as we did for our linear problem. We start with the trivial constraints, which are essentially that the performance of the CPU is smaller or equal than the peak performance of the CPU, and performance of the GPU is smaller or equal to the peak performance of the GPU, as well as having every flow in our flow network be smaller or equal than the corresponding peak theoretical sort of flow that that specific hardware component supports. And from here, again, we enforce this continuity constraint, and we compute all of the inequalities that are enforced by these transfer intensity quantities. It's a little bit overwhelming, but it doesn't matter. The point is that you can do the same exact thing as we did for the linear example and derive some constraints or project these constraints on both the final performance of the CPU and the GPU. And you get one of these constraints for each component in the gracehopper node, each edge in the network, essentially. Now, I want to look at one specific path, which is the one that goes from the slingshot network to the GPU performance. Specifically, I want to take a look at the constraint that this peak sort of bandwidth beta 1 imposes on the final performance of the GPU. The computed constraint that we got at the previous step was just that the GPU performance has to be smaller than the intensity, the operational intensity of the GPU, multiplied by the transfer intensity from 3 to 7 and from 1 to 3, finally multiplied again by this beta 1 peak bandwidth. And if we actually sort of apply the definitions of intensity and simplify, well, it turns out that really the performance of the GPU is directly limited by sort of the ratio between the compute that you're doing on the GPU and the flow that is the flow of data that is traversing this the first edge, this edge where beta 1 is defined. So in a sense, the conclusion here is that each component can enforce its constraint via an operational intensity that is defined as the performance ratio to the number of data that is being transferred over that specific edge. So we don't actually need to go crazy and build all of these complicated graphs, because at the end of the day, the topology of the data simply enforces a constraint in terms of, the topology of the system simply enforces a constraint in terms of which intensities you're considering, because everything simplifies out. So summarizing, I wanted to just give a little bit of a summary between the traditional roofline analysis and our approach. First of all, we said that the traditional roofline analysis assumes a single or uniform sort of kernel execution, while in our case, the workload can be heterogeneous and time-dependent. That's absolutely fine. In terms of traditional roofline analysis, they use a static intensity and performance, so the workload is represented by a single point, while in our case, we have dynamic intensity and performance. Again, the workload in the classic case, or the classic model, is represented by a single point. In our case, as I showed you, as a distribution of samples over a roofline plot. The traditional model, the hardware hierarchy, shares a single operational intensity that is many times, for example, computed just by analyzing the algorithm by hand, while in our approach, each single component of the node enforces its own operational intensity and sort of projects its own constraint on the final performance via this quantity. Again, as I said, in the classic case, intensity is often estimated analytically, while in our case, intensity is always estimated by measuring data flow in the system. So you don't actually have to go into your code or analyze what's going on, which for many workloads using different, for example, machine learning libraries, becomes unfeasible. There's just so many kernels, so many things going on that there's no way you're going to be able to track of the memory movement by hand and derive an analytic solution for this. And this brings me to talking about bottlenecks and efficiency. We spent a lot of time talking about how to project these performance constraints, and now the question is, how do we use them to derive more meaningful metrics that we can use to understand what is going on with our workload. Now, as I mentioned, each component generates its own operational intensity, which in turn generates its own sort of roofline plot. And so we need a way to aggregate this data. What is sort of interesting here is that given that every component projects an upper bound, there is always a tightest upper bound among all of these components. In the case of this example graph that I showed you, the ith edge, which has operational intensity II, bit of a poor choice maybe, in this case is the tightest bound in the beta II portion of the graph, so the blue part, blue area. But as soon as you cross a sort of reference point, which is very similar to what we had in the classic example, we cross into a region that is bounded instead by beta k ik. So essentially, you have different components that are competing in order to become, the bottleneck, the pain that you're trying to optimize away, in a sense. So let's denote the tightest upper bound as U, which is just the minimum between all of these beta I, II, or whatever, as well as, of course, the peak performance pi. I want to define the attainable efficiency as the performance that you're getting over the tightest upper bound. And essentially this tells you, given a situation where I have a set upper bound on the achievable performance, how close am I actually getting to that theoretical upper bound? So that's sort of what the attainable efficiency tells you, because in theory, if you had perfectly optimized code, you would be able to reach, let's say maybe 90, 100% of attainable efficiency, since that's the upper bound that you can get to with this sort of set of constraints. And then I want to also talk about ceiling efficiency, which is the ratio between the upper bound and the peak performance pi. And this tells you instead how close your upper bound is to the maximum theoretical peak performance of the GPU, so to being completely compute bound. And then, of course, the total efficiency is just a product of the two and is essentially performance over the maximum performance of the GPU. This is not super interesting because it just tells you, in a sense, how much raw power you're using from the GPU. And if we look at the graph for a moment, I want you to imagine these 2 points. You run your workload and you obtain these 2 points on the graph. The attainable efficiency is essentially, you can see it as the distance that you got up to before hitting the line. For example, In the left point, in the blue region, you can see that the tightest upper bound is the blue line directly above it. So if you look at the height sort of in the performance axis of that point, you're about 80% there to getting the very maximum performance that you can get to. And the same goes for the other point in the red region. It's about, in that case, the sort of performance, the tightest bound is the horizontal red line, and you're about 80% of the way there. So in both cases, you have about an 80% attainable efficiency. Now, the ceiling efficiency instead quantifies how far away your constraint is from the compute peak capabilities of your GPU. So essentially, you can have situations where the attainable performance is the same, but since the ceiling sort of performance is completely different, well, in reality, you have a well-optimized code, but your workload simply needs a lot of data movement compared to computation, and that's why you're not able to squeeze out more performance from your GPU. And of course, here, yeah, it's the total efficiency. It's just the ratio of how close you are to the peak performance line. So in one case, it's about 30% of the way there. In another case, it's about 50% of the way there. Okay, so these are some workload efficiency plots of the mystery workload that I showed you before. Now, you can see that the attainable efficiency is almost always 100%, right? It's roughly around 75%, oscillates a bit, but the point is that when you have an attainable efficiency of about 100%, you know that your code is running at the maximum achievable performance for your given workload. So your code is well optimized. On the other hand, if you have a ceiling efficiency of 100%, it means that your workload is essentially compute bound. And the more you get away from this 100%, the more your workload becomes data movement bound. And again, yeah, if you have a ceiling efficiency of less than 100%, then your workload is data movement bound. And what can happen is that you have a very high ceiling efficiency, so your workload is compute bound, but your attainable efficiency is very low. And in that case, there are sort of two intuitive explanations for this. Either your code is poorly optimized, and it's just not running well for whatever reason in terms of actual implementation of your workload, or the bottleneck is simply something that you're not modeling or not taking into account. So for example, in this case, we're taking into account NVLink and memory bandwidth only, and maybe the bottleneck is something that goes on in the network, and you don't see that, so that's what's actually imposing a constraint on performance. And in this case specifically, you can see again that the attainable efficiency is about 75%, so the code is well optimized, but most of the time the ceiling efficiency is 0. So it is extremely memory bound, meaning that it is well optimized, it's just that you're moving a lot of data compared to the compute that you're actually doing. And so again, here is just another plot for something that is compute bound or more compute intense. You can see that in this case, the ceiling efficiency is very high, and the attainable efficiency is also very high, meaning that your workload is both compute bound and very optimized. And so again, the rule of thumb here is that attainable, how well optimized your code is, ceiling, how much the workload relies on data movement versus computation, and the total efficiency is how much raw compute performance you're using out of the GPU. Here's just some example data from an HPL run that I did on 16 GPUs using 4 nodes of the CSCS out system. I wish I could have shown you more data, but unfortunately time was tight, so I only have this HPL example to show you. As you can see, GPU utilization, again, fixed at 100%. Then you have some other sort of metrics like occupancy and memory activity, which are both low, under 25%. The SM activity and the tensor core activity are sky high, almost 100% the whole time. And the NVLink data transfer sort of gradually increases up to about 40 gigabytes a second. And so what we can do is we can take all of the mathematics that we did sort of earlier and apply them to this case, and what we get is essentially this efficiency graph, where you have a time series for all of the GPUs. The gray area is sort of the maximum and minimum values that were encountered throughout the workload. And each section of the graph is sort of colored based on whether it is compute, memory, or NVLink bound. I'm using a slightly simpler model here for the sake of the presentation. And I'm just treating NVLink as one single sort of constraint or upper bound. But really, there's no problem. I could theoretically split every single NVLink lane and measure every single one independently, so I know exactly, for example, if data transfer between a specific pair of GPUs is the limiting factor in my efficiency. And again, what I wanted to point out is ceiling efficiency 100% almost all the time, meaning that it is almost always compute bound. You can see that it matches very well with the red line. And then the attainable efficiency is still quite high. It sort of kind of sways downwards to the end when the amount of data transfer increases. But overall, it reflects quite well the total efficiency, which essentially tells you that you're melting the GPU, essentially. You're using almost all of the compute capabilities of the GPU. Now, I'm getting near the end of what I wanted to discuss. Very important to touch on limitations and sort of future work that could be implemented into this performance model. I want to start with discussing what this model can do. And what it can do is it can help you identify bottlenecks in your workload, so which component exactly is slowing you down. It can help you evaluate the efficiency of a specific implementation of an algorithm or workload. And it can help you compare the performance of different workload configurations or parameters or input files depending on what you're doing. What this model cannot do is compare fundamentally different algorithms. This is not a magic sort of metric that lets you say, oh, this is better than that. A very simple example is if you're doing any type of scientific computing, you could choose whether, and you're solving, for example, a linear system, you can either go with sparse or dense LU factorization on GPUs. If you're doing dense LU factorization, it's basically what HPL does. And so you'll have very high efficiency, very high values. It looks like you're melting the GPUs. But of course, if your system is sparse, it's much better to use a sparse solver, which is way less efficient, has way uglier or less impressive metrics, but is still way faster because it is a fundamentally different algorithm that makes use of sort of additional knowledge of your problem. So again, you still need to pay attention and ensure that you're doing an apples to apples comparison and not just comparing two fundamentally different things that are not comparable. Now, in terms of future work, there are a few things that this model is still missing. First of all, currently we cannot measure or we don't have an implementation for this. We have not yet integrated the efficiency and bottleneck analysis of network, NCCL, and MPI components. In theory, there is no problem in doing this. It's just that you need to actually write the code to have something that collects this data. And in theory, that's probably not a good idea, but in theory, you could extend it to every single component in your whole supercomputer and use the same exact sort of technique to project the performance bound from every single compute component, or from every single component to the compute capabilities of your GPU. And another one is try to integrate somehow a broader number of metrics. For example, I did not use, or we're not currently using SM occupancy, which is a very good indicator of how well you're overlapping data movement with compute, which is, of course, a critical thing in machine learning tasks. We still have to find out or figure out a way to incorporate this mathematically into this type of performance model. So I want to give some final remarks from my side. Of course, this will not be the end of the presentation because Nina still has to discuss a lot of interesting things, but from my side, what I wanted to recap here is that Nvidia GPUs offer a cheap way to track hardware activity by reporting these point-wise averages over sampling intervals. And we can use this data to build sort of a generalized dynamic roofline analysis of the algorithm, where performance and operational intensity are seen as time-dependent quantities that vary in the workload, and where we incorporate sort of the topology via this flow graph interpretation of the problem. Again, each component enforces a constraint on the final performance, and the bottleneck is essentially the tightest upper bound that you can derive. And in the end, we define these three sort of efficiency metrics that tell us how well optimized the implementation is, how much data movements versus computation affects sort of your workload, and how much raw performance compute, or sort of raw compute power you're using with a specific workload. So from my side, that's it. And now I'm happy to pass on the word to Nina.
Hi, thank you, Marcel, and this was actually an interesting part. I'm just going to go over the housekeeping now and the practical side of things. So again, my name is Nina Mujkanovic. I'm a machine learning engineer with CSCS, and as part of the team that's working on machine learning, you will realize that in the spirit of collaboration, I have stolen a number of fuzzy slides. It's part of my coherent story, or our coherent story on the machine learning platform, and the GPU saturation tool is part of the machine learning platform. So as mentioned previously in the table of contents that I know you will not remember currently, I'm going to start with just describing what the system is like, why we're even where we are at right now, what the use cases are, what tools are available to look at the GPU saturation, what we have decided to work with, and finally give an outlook of how we're going to continue this work. So what is the Alps research infrastructure? It's a heterogeneous supercomputer based on HPE Cray technology, so it's a Cray EX, and you've already heard all of this before. It has a power envelope of 11 megawatts, and it has versatile clusters, so dedicated partitions with tailored software environments for various users that we will get into partially later. So it has multiple architectures. It has 1,024 multi-core nodes with 2 AMD Rome processors. What's important for us in this conversation is that it has 2,688 hybrid ARM64 and Nvidia nodes, which with 4 Nvidia Grace Hopper superchips per node comes out to about 10,752 GPUs, so it's a pretty large system. It has 6.9 petabytes of RAM and some additional special purpose nodes. And of course, finally, there are 128 hybrid MI300A nodes, which we will not get into here because it is kind of an NVIDIA GPU specific talk. So what does the system look like? This is just a simple schematic from HPE where you can see the entire system exploded with the compute chassis move forward and the compute blades. Each of these blades has 2 nodes, which you can see here covered in red. So these are the GH200 blades. And in each of these nodes, you have 4 GPUs. So what is the Alps Grace Hopper module? There are 72 ARM Grace Hopper CPU cores and 1 H100 GPU. 128 gigabytes of host memory, 96 gigabytes of GPU memory, and has the fast chip-to-chip link with 900 gigabits per second. That should be a B. And current power limit of 624.15 watts. So in this case, the GPU and the CPU share the power budget, but the CPU has precedence over GPU, and I'm just bringing up this entire conversation on power because it is part of the efficiency of the system, part of why we also want users to use the GPUs to saturate them as efficiently as possible. And you've already seen the schematic in Fozzy's presentation, so I'm not going to go in depth into it, just going to point out that there are 4 Cassini switch NICs per node, so 8 per blade, and all of them are connected to, as you see in the back, the switch chassis and the switch blades. And these, across the entire system, are of course connected to a Dragonfly network topology. So you probably also know this one pretty well. It's a low diameter direct network with no external fat tree top switches. There are 3 levels of connectivity. You have the edge links with the nodes to the local routers. You have the infragroup links with the routers within a group. And finally, you have the intergroup links with optical connections between the groups. So the idea is that you should never be more than 2 hops away from any given point within the system. Well, 3 hops, I correct myself, between any component within the network. Now, as Marcel previously mentioned, there was no modeling of the network within the tool in its current configuration, but that could be one of our future goals, integration of also these components. So how did we get here? Why are we even discussing a GPU system? Why do we even have this many GPUs within an HPC system? So there has been pioneering work done regarding accelerated computing at CSCS. So we deployed the first GPU supercomputers in 2011. That was Switzerland's first petascale system, but also Europe's first GPU-based supercomputers. And it played a pivotal role back then alongside with Ornell's Titan in the early adoption of GPUs for HPC. A lot has happened since then, especially with the explosion of LLMs and their compute needs. So 2011 was still kind of the last point before deep learning really took off, especially with the 2012 AlexNet that basically took old modalities and put them on new systems and really showed what you can achieve by, let's say, in a sense, taking an old wheel but putting it on a new machinery. So on the left, you see the verification loss of some unnamed LLM. We don't really care. The point is here really to point out that even in this example, the validation loss can take petaflops per days to actually decrease to the convergence level that we want. And on the right side, you see training compute of notable models from Epoch AI, where you can just see the linear scaling when you look at the publication dates of models such as AlexNet, GPT-3, GPT-4, and so on, across the flops that they require. And what's interesting to point out here is that Alps has, or we have with Alps, kept up with this scaling in a sense. If you look at GPT-3, I have a pointer here, don't I? No, I don't. I cannot point to it, but if you look at GPT-3, you can see that it's barely below the line of what you require. Well, it's barely below the line of 10 to 24 flops, which is one day on Alps at 100% efficiency with F14.16 tensor core training. So training these models requires a lot of performance. And that's where we get into Alps. So this is just a continuation of pioneering accelerated computing. The hardware at that point in time, when the contract was agreed upon, did not exist. The GH200 did not exist, and the AI boom had not yet started in full. But we feel that it has kept up with the requirements of the field. And Alps currently, or at least maybe with some outdated data, with the GH200 partition, was Europe's largest and greenest supercomputer in 2024 for a while. Europe's most capable open AI supercomputer, or maybe let's call it our stated goal. And we were also NVIDIA's launch customer for GH200. So from a practical use case, I would just like to point out that hardware development kind of also followed software needs software development, but now the hardware that we have also pushes what we can do with it and the users that we have. So some of the practical use cases we see for having such a GPU saturation tool, saturation scorer tool, is for ease of users to, for example, work out their requirements when they're requesting resources on the system. So we have the user lab where we have researchers submit scientific project proposals for resources, and these then get peer reviewed. And again, we need to see what they project are going to be their needs on the system. We have the Swiss AI initiative, which has been awarded compute time around 45% of the GH200 system time. Again, it's good to know how efficiently the researchers can use the system. And I will not talk about the verticals, but you've also already seen that in Fozzy's talk, and you have seen one of the verticals in Emmanuel's talk earlier today. We also have the PASC, Platform for Advanced Scientific Computing, where again, it would be useful to have such a tool to help us distinguish what the user needs are and to as efficiently as possible allocate time. So how do we go about this? How do we go about profiling NVIDIA GPUs? The profiling is not trivial, at least not for a new user. It can be quite confusing, but a number of tools do exist, and I'm only listing here NVIDIA-specific tools. So you have the Nsight tools, Nsight Systems, and Nsight Compute. And you have some other tools like PyProf, which has then developed into DLProf, or rather PyProf has been abandoned for DLProf, and you have the GPU profiler. So looking at these systems, I'm just going to point out we did not choose any of these for the GPU saturation score. So regarding the Nsight systems, it's a system-wide fine-grained performance analysis tool, but for our needs, it just produces too much data. It produces timeline view for any quantity of CPUs and GPUs. And it can lead to such situations that you have extremely long kernel names for applications with if they have many nested levels of namespaces. So the image is from the Nvidia blog, and you can just see what the interface looks like. And when I saw it for the first time, when I just started using it, it was extremely confusing to me. And I would posit that it's also extremely confusing to a lot of users who are coming from a non-HPC field or from a non-hardware near field. Then we also had Nsight Compute, which is the kernel-specific, very fine-grained performance analysis tool, so the pendant to the systems, where we also had some issues with the granularity levels because it is so fine-grained. It adds a significant overhead, and it makes it unsuitable for our profiling needs because profiling entire workloads, particularly large distributed ones, just would be too significant for the system. So again, this is an image from the Nvidia blog, just exemplifying what the tool looks like. Finally, we looked at DCGEM, and DCGEM is the data center GPU manager. So it's an open source project that enables easy GPU performance monitoring, and it offers access to hundreds of metrics, potentially thousands of metrics, depending on the system, for the Nvidia GPU drivers. It can offer metrics such as temperature, power consumption, memory usage, and whatever you can think of. So it offers easier ways to profile the metrics and handles communication with NVIDIA drivers. On our side, this is basically the foundation of the tool because it introduces little overhead, so it has minimal code change for users, and it has a few simple to understand but relatively important profiling metrics. There are some limitations with this tool too, of course, because there are so many potential metrics you can look at. It's not really adequate for users. And because you sometimes need root permissions, it's basically really designed for system administrators, and it's a bit harder to integrate with Slurm. So if you look at if you look at the offering that we saw as a potential for this tool, from Nsight Compute to Nsight Systems to DCGEM, this is the mental model I would suggest, where DCGEM is at the highest level. It gives you the most information, the most metrics, if you want to look into them, but you can choose. Then NSYS, which again looks at the entire system, all the way down to a lower instruction and the kernels of the NCU. So going back to the first slide, I did not mention DLProf here because it's an application, it's very application specific to deep learning workloads, and we wanted this to be basically disconnected from any specific workload. Sorry. And I also did not mention GPU Profiler anymore because it was created by an NVIDIA engineer, but it's not affiliated with NVIDIA, so he did it in his spare time. It looks like an easier to use tool to visualize what you have going on with the GPU, but there have been no updates since 2021. So what are the challenges that we have when we're even looking at the GPU saturation and what the user has running on the system? The main challenge here, in particular with machine learning, is that we have distributed workloads. We have data parallelism, we have model parallelism, we have hybrid modes between these. We have different models of use. So running distributed workloads is really non-trivial, especially for a user that is new to HPC, but even to more experienced people. And when you take into account that we have a container-first approach, we're adding another layer of complication to this. So we have container integration with Slurm, which requires the Pixis plugin, but we also have UMs. And I'm not saying that these are negatives, they're positives, but there is more work to be done in order to integrate any kind of tool to to optimize distributed workloads. Then we have additional challenges for users, such as access to shared memory, communications. Do they use NICL? Do they use MPI? Parsing of GPU analysis data is really not trivial for novel users. And finally, the question is really, how do new users fill GPU? So we just came up with the GPU saturation score. The name is still to be decided. That's not going to be the final one. And the goal was really to simplify and streamline the collection of GPU metrics. So basically, offer key features to the users such that they can run with minimal code changes, have simple options that are easy for them to understand, very little overhead so that they can actually profile real workloads, offer them Slurm and MPI integration so that they don't have to faff around with that, and give them an automatic data analysis result. So really, a metrics overview that summarizes everything, a time series averaging and visualization, as you've already seen, and load balancing visualization. So these are all of the examples that Marcel already brought, and that came from the tool. So final slide, what is the outlook? At the higher level, we're really looking to create a tool from the HPC community for the ML and broader community for the users so that they can have a simplified tool that is satisfactory to a broad base. It's not going to satisfy power users, but the idea is really to simplify things for the average user. We're looking at tighter integration with the ecosystem, so curated user environments for machine learning workloads that offer improved workload observability with systematic node vetting, and finally the GPU scorer directly for the users so that they can optimize their workloads. We hope to integrate at the lower level the GPU saturation tool in the existing infrastructure, so use the elastic database store metrics instead of individual user collections, and just overall improve the usability with actionable feedback loops from the user community. So visualizations of heat maps to simplify usability, or integration with visual interfaces delivered via web interfaces. So yeah, that's the talk. Thank you for listening. Marcel will answer the first questions because I have to cough.
Any questions? And I guess we're going to start with Marcel.
Just apologies, a stupid question, but in the end, what was causing the modified Adam to go faster 20% with respect to the standard?
Okay,
ones?
yeah.
Because I remain with this curiosity.
Yes, so the difference is basically in how the whole algorithm is laid out. In the standard Adam implementation, you have different kernels that are called back and forth from the CPU to the GPU, and so a bunch of data movement occurs. While in the fused implementation, you have one big GPU kernel that does everything, the whole sort of Adam pass. And so you move the data to the GPU, and you do the full sort of iteration of Adam, and then you move back the results. So essentially, if you were to apply this model to this specific case, you would see that the fused Adam has a higher ceiling efficiency because it does more computation per movement between GPU and CPU, and of course also probably a higher attainable efficiency because it's sort of better optimized to run on the GPU.
Regarding how you plotted the SM occupancy. There are like 132 SMs on a H100 GPU, and it is possible that during a certain run, you have some SMs running kernel 1, some SMs running kernel 2, and some SMs actually being idle.
Yeah.
So what do you mean by SM occupancy in this? Is it one particular SM that you are looking at, or is it a global metric?
It is a global metric that is computed by DCGM directly, and it involves a bunch of different factors that are not even fully explained in the documentation. So essentially, it is a quantity that is used to sort of tell you, on average, over your SMs, what is this ratio between resident warps to the maximum number of resident warps. But and by resident, what they mean, or what I think they mean, is basically your kernel is loaded in the registers and is ready to execute, but is not actually computing yet. So that's how it is. But it is not only tied to the hardware of your GPU. It also depends on how you're launching your kernels. So depending on how you specify, for example, grid sizes or all these, tiny details, the computation results into something different. Unfortunately, I don't know how it is computed because it's not documented. I would have to go and look into the DCGM source code to find out. But yeah.
Any other questions? Any questions for Nina? Okay, thank you very much.